In this video, we're going to continue our coverage of basic discrete objects, the kinds of discrete objects that we see a lot in computer science and discrete math. And this is going to just, again, be a review for many of you, but it's important. So a fundamental object that we're going to look at and see again and again is the binary relation. And this is another one of these topics which is for some reason taught sometimes at high school and middle school levels in a very specific algebraic way that makes you think that it's a statement about real numbers. But I want to make sure that we have a clear idea about what the general notion of a relation is, especially binary relations. So when we have a pair of sets, a binary relation, let's call it R, is really just a subset of the Cartesian product of the two sets. That is, it's a set of ordered pairs. And the kinds of relations you might be used to working with, you might not think of them this way. But for instance, if you took the natural numbers and you took, let's say, the less than relationship, so let's take this pair, right? There's the set and the relation. In this case, it's a relation on n cross n, right? It's a subset of n cross n. There are some elements of that product. There are pairs of numbers, for instance, 2, 3, would be in this set of pairs, right? Because, and this is a terribly weird thing to write notationally, but I'm treating this symbol here as a set. And we're never going to do this again after today, but just to remind you the types of objects, right? This is 2 is less than 3. You see, because we write relations most of the time, especially binary relations, in this what we would call an infix notation. Infix in that the relation symbol goes between the two operands. And you can also think of this as a function, which is really like a function of two elements which returns either true or false. So it's like the membership test. And actually thinking about relations as functions can often be more useful. All right, so that's just what the binary relation is. And again, if x equals y, right? If it's the same set, i.e. R is a subset of, say, x cross x, this is sometimes called a homogeneous relation, binary relation, and in this case we'll say like R is a relation on X. Now for a binary relation on a single set like this, there's a couple properties it might have, and these are important enough to have names. One is the reflexive property. So a binary relation is reflexive if for all the elements in the set, the element is related to itself. And for general binary relations, sometimes I like this tilde symbol. Okay, so x is related to itself for all x in x. So it could be symmetric. And this would mean that if x is related to y, that would imply also that y is related to x. Right? So if they have the relationship, then the relationship is symmetric. You could swap it around. It's still true. There's another very closely related property that some relations have, which is being antisymmetric. And this one you have to be a little bit careful about how you define it. You might hope that it just means that this implies, say, not this. And that's not quite it. I'm going to write it like this. It's going to say that if x is related to y and y is also related to x, that can only happen if x and y are the same. Okay, and this is going to allow us to have relations which are both reflexive and antisymmetric. And let's see, we also want transitivity sometimes. Transitivity is a good one because this is the one that says, if x is related to y and y is related to z, then x is related to z. Tremendously useful. This is in relations, this is what allows you to do something like what we did with composition for functions, right? This is like composing the relation, right? Because x gets to y, then y gets to z. You get straight from x to z. And the last one, I'm going to call it complete. This is not the standard term. I think people often call this technically a connex, which is a sort of a strange word because it sounds a little bit like connecting. It sounds like almost like convex. It sounds like too much like too many other words, and it's not used widely enough. But I think the message gets across if we call it complete. And this is where, either x is related to y, or y is related to x for all x and y. All right, for any two elements of the set, you have at least one of these relations has to hold. Okay, so this is our basic properties we want to look for in a binary relation on some set. Okay, and we've already seen some of these. One of the more important classes of relations that you will encounter are equivalence relations. And this is just going to be, again, this is a binary relation that have some of these properties, right? There are really three that determine an equivalence relation. It should be reflexive, symmetric, and transitive. And the canonical example you can keep in your mind for what an equivalence relation should be is, well, pretty much anytime you use the equal symbol, it should really have this property. For instance, if I took, let's say, the natural numbers with this equals relationship, you know that for all numbers n is equal to n. That would be symmetry. Oh, sorry, that's reflexivity. We know that if A is equal to B, then B is equal to A. Sorry, let's get this right. This is reflex. This is the reflexive property. This one is symmetry. Get these right. And then transitivity is also pretty well known, right? A equal to B, and B is equal to C. This implies A is equal to C, and that's transitivity. Okay, so we have pretty much anytime you use this equal symbol, you're going to have an equivalence relation. And really, you should never use this equal symbol for anything which doesn't have these three properties. Although I guess the one big exception for this is something is equal to big O of something, which is just a problem with the big O notation, which unfortunately we can't fix right now. This transitivity of equality, this is well established. It goes way back. If you were to dig into your old volume of Euclid's Elements, because hopefully you have an old volume of Euclid's Elements, you'll find right in the first or second page in his Common Notions where he describes transitivity of equality. It says something like, if two things be equal to the same thing, then they're equal to each other. And this is actually the part of Euclid that Abraham Lincoln quotes in the Lincoln-Douglas debates on, the equality and rights for slaves, etc. So this kind of has also some historical importance, and you will see other equivalence relations besides just equals. In fact, lots of them. In fact, we've already seen one. Right, we talked about isomorphism of sets. So you can check. I'll leave this as an exercise. That isomorphism for sets is an equivalence relation. So you can check that one as well. Right, so anytime you're asked to do that, to check that a particular relation is an equivalence relation, as long as it is a binary relation, you just check these three things. Is it reflexive? Is it symmetric? Is it transitive? So oftentimes these proofs have three parts, one for each of the properties. All right. Another cool kind of relation that we're going to encounter quite a bit are total orders. These are binary relations that are complete, reflexive, transitive, and antisymmetric. Okay, and this antisymmetry is capturing the ordering. Okay, and you can check maybe the canonical example for this would be something like, let's again take the natural numbers with the less than or equal to relation. So it's definitely reflexive. We saw that already. We know that for any two numbers, if I have a and b that are natural numbers, it's going to be the case that a is less than or equal to b, or b is less than or equal to a. Okay, so it's definitely complete. Reflexivity, we already saw that, well, we can check this, right? A is less than or equal to a. That's our reflexive property. It's going to be transitive, a less than or equal to b, b less than or equal to c, a is less than or equal to c. And transitivity, right? If a were less than or equal to b, and b were less than or equal to a, if both of these are true, then a really does have to be equal to b, right? Because otherwise, if they were different, then one would be strictly bigger, and therefore we put these together and chain these together, and we'd find that a was strictly bigger than itself, or strictly less than itself, which is impossible. This gives us all our properties, and that's kind of the standard example of a total order that you can keep in your mind. And you're probably comfortable with this from other settings. Now, I listed these four properties here. I could have left this one off, which sounds a little weird because maybe it seems like it ought to be an important property. But when I say I could have left it off, I just mean that actually any complete binary relation is also reflexive. Let's just check this. I'll write it as a lemma. Complete binary relation is also symmetric, is also reflexive. So we didn't actually have to write down this as one of our properties in the definition of a total order. We could have said, hey, it just has to be a binary relation that's complete, transitive, and antisymmetric. The proof is really simple. It says, hey, for all x in whatever our, let's call it x. So if it's a binary relation on some set x, we know that if it's complete, right, that implies that, well, I need a pair of things here. Oh, maybe I'll get away with just one. So it means that x is related to x, or x is related to x. Does it fit on the paper? Yes, okay. So one of these two things is true. I can write it bigger so it actually shows up on the video. Right, and so, but if I have the or of these two statements, and these two statements are the same, so it implies that x is related to x, and that holds for all x, and therefore this is reflexive. Now, I could have left it out, but I didn't, because it's really handy to remember that when we talk about orderings, even though it would be nice to think of strict orderings, most of the time when we ever say a total order, it could also includes reflexivity, which means it's the less than or equal to. And actually, if you took, say, the strict less than, this is not a total order, which seems a little weird, perhaps. It is sometimes called a strict total order, but according to the definition, it's not a total order because it's not reflexive. And you might think this is a better example of one, but really this completeness is important. So if I have completeness, I'm definitely reflexive. But we can get rid of, in fact, both of these properties, and we arrive at a different concept, which is called a partial order. And so this is just going to be, well, actually, we won't get rid of both. This is going to be only reflexive, transitive, and antisymmetric. So you get from a total order to a partial order just by eliminating this requirement that it's complete. And what you end up with is a relation, a binary relation, where there are pairs of elements of the set that are not related in either direction. Right? If you lose that completeness, there might be these pairs. And I think the canonical example for this is if you were to take, say, a finite set X and you take its power set, and then you take this subset relation. So let's define X to be A, B, and C. I'm going to use a sort of shorthand for its power set. Technically, there's 3 elements here. So the power set has 2 to the 3 equals 8 subsets. And I'm going to write the subsets as just strings here because it saves me a lot of curly braces and commas. So there'll be ABC, AB, AC, BC, A, B, C, and the empty set. Don't forget the empty set, and I forgot to tell you this before. Of course, the empty set is a subset of any set, and if you want to write it in LaTeX, you would write \empty set, right? So you wouldn't write \phi or something like that. So here are 8 elements. Let's double check. Sanity check this. 1, 2, 3, 4, 5, 6, 7, 8. If I wanted to draw out the subset relationship between these, one thing I might do is just draw them as directed arrows, right? So AB is a subset of ABC. AC is also a subset. BC is a subset. I guess I have A, B, and C as well. I can start drawing these. And here. And empty set. This isn't all of the relationships, I guess. I have a couple others. In fact, anytime you can get, because it's transitive, anytime you can get from one to another, there should be another arrow. So technically, I'm going to have an arrow going all the way up here. Well, there's an arrow from the empty set to all of these. There's an arrow set from all of these. It starts to get to be a bit of a mess, but those original dark arrows I wrote, it's a way of drawing partially ordered sets as a set with a partial order called a Hasse diagram. And we're going to talk about these a lot, so you don't have to think about it too much right now, but we'll get into it quite a bit later. In terms of being a partial order and not a total order, it's really clear that AC is not a subset of AB, but also AB is not a subset of AC. If we want to check the other properties, it's pretty clear that they're going to hold, right? Every set is a subset of itself, so it's reflexive. If you're a subset of a subset, right, then you are a subset of the last thing, that's transitivity. And antisymmetry, one of the ways we defined equality for sets, that is to say, if I have a set X, I already defined X, let me pick a new one. Let's say I have S, if it's a subset of T, and T is a subset of S, then from these two, we would imply that S is equal to T. So that was, in a way, how we think about equality of sets as being subsets in both directions, which is exactly the antisymmetric property. So once you have this definition, then you know that antisymmetry holds. Technically, the definition comes first, but we use that to show that this relation does have this antisymmetric property. Whew. Okay.